Alright, let's take a look at transformations. So I'm just going to kind of summarize how to perform transformations, the different types of transformations, how to change one graph to the other, as well as this notion of mapping notation, which is really useful in looking at transformations. Right? Now, in this sense, there's basically, for transformations, I like to look at transformations as two types. Okay, so transformations can be grouped as modifications, and modifications will change the shape of the function. And there's also translations. Translations change the position of the function. Okay, so I like to think about modifications as two main branches: stretches, shrinks. Right? You can also call stretches expansions. You can also call shrinks compressions. Right? And there's another group of modifications, right, which are called reflections. Okay. And all of these transformations will have to do with x or y values, right? So we can have stretches or expansions on the vertical, which is the y values, or the horizontal, which is the x values. Right? It's the same idea with shrinks and compressions. We can have vertical shrinks, right? Or we can have horizontal shrinks or compressions. Okay, and translations, we can also affect them on the vertical and the horizontal. Now for reflections, right, a vertical reflection, I'm going to just kind of show you guys really quickly what a vertical reflection is. Right, so like if this a vertical reflection, if you have a graph, and let's call this guy f of x, a vertical reflection is a reflection over the x-axis or in the x-axis, and you're going to basically have a graph that looks like this. This is negative f of x. Okay, so you can notice here that we have the same x values, we have opposing y values. Okay, so like if we're looking at this value, this is x and this is y, right, this is going to be x and negative y. Okay. So this is what we call a vertical reflection. Now a horizontal reflection is going to look kind of like this. Okay, so in this case, instead of x, we have negative x. Okay, so green, we have a horizontal reflection. This is going to look like f of negative x. Okay, so these are just some examples of transformations, but what we're responsible for, and you probably have looked at this in previous grades, if you want, you should review some of the videos that I have about transformations, what they are, if you need a much more detailed refresher. But what we need to look at right now is a functional method of demonstrating transformation. So we want to look at transformations, g of x as a transform function, f of x as a parent function. So we're transforming f of x into g of x. Okay, it doesn't matter what functions you use to be the parent and the transform function. Okay, but we're going to look at this template as g of x is equal to a f of k x minus d plus c. Okay. And you might see this using different variables. These are just the variables that I've chosen to use, and I'm kind of correlating it with this excerpt I got from a textbook. Okay, so in this case, a here is your vertical stretch or shrink factor, and all of this is kind of mentioned in this excerpt, right? K here, well, 1 over k is your horizontal stretch or shrink factor. D here is for the horizontal shift. C here is the vertical shift. Okay, and you can kind of correlate this with some of the terminology that's found in this portion, right? Looking at A, if A is greater than 1, then in the graph y is equal to f of x is stretched vertically by a factor of A. Factors means that we multiply whatever the x or the y value is by that value or that factor. Because A is a vertical stretch or shrink factor, it's going to multiply the y values. Now, when A is a fraction, when it's greater than 0 and less than 1, the graph is compressed vertically by a factor of A. When A is less than 0, the graph is also reflected in the x-axis, okay? The value of k determines whether there is a horizontal stretch or compression, right? So when k is greater than 1, the graph is compressed horizontally by a factor of 1 over k. So compressed horizontally means that we're basically shrinking it horizontally, right? So if you're shrinking it horizontally, the shape of the curve will get longer and narrower. And when k is a fraction, the graph is stretched horizontally by 1 over k. Okay, and when k is less than 0, the graph is also reflected in the y-axis. Okay, so for values of d and c, d is your horizontal shift. So if d is greater than 0, right, we have a shift d units to the right. D is less than 0, we have a shift d units to the left. Conversely, for c, this is a vertical shift. So if c is greater than 0, then the graph is shifted c units up, and if c is less than 0, the graph is shifted c units down. Okay. So using this notion, we can think about all of our transformations for g of x as transformations from f of x. So actually, before we look at g of x, if we consider points f of x, if f of x has the points x and y, then g of x is going to be some kind of transformation to x and y, right? So if we're looking at transformation of f of x into g of x, right, we can look at this template where for the y values we can have a vertical stretch, so a times y values, a vertical shift, c units up or down, so I'm going to use plus c. For the horizontal values, we can have a horizontal shrink or stretch, and it's always by a factor of 1 over k, so I'm going to write 1 over k here, and this is going to be either a shift d units right or left, so I'm going to do plus d here. Okay, so this is basically what we call mapping notation. The mapping notation creates a transforming equation. Okay, so the mapping notation creates a transforming equation where we can change our original values of our parent function into our transform points on our transform function. Okay, so I'm going to show you guys examples of that, right? But make sure you can keep this little excerpt here. It has all of the rules that you basically will need to kind of work through these transformations.